Great. So we are talking about data science. We had the motivation for the why do we care about data science, and why some of the things that we are doing are still relevant, even with ChatGPT or similar generative AI. Then we talk about some basic tools. We talk about probability. You cannot do data science without probability. And this set of slides that we talk about them essentially here, I think is a very good cheat sheet that you can just go there if you have some interview, etc. These are super important. As I mentioned, the main motivation for A/B testing, that's one of the things that you need to know probability theory there. Otherwise, I mean, essentially it can be very costly for the company if it's just doing some exercise, some test, which is not good. What else? We talk about probability in Python, especially we talk about colab.research.google.com, that you should go there. And this is also for Jupyter Notebook. That's a very good place to do that. You don't need to install it. You can just use it. So that was one tool. The other tool that I want to talk about it is today about linear programming. So linear programming is a way that if you know about it, then you have a much more, I mean, essentially, like edge comparing to the other people in a company. Why? This is the somehow comes to this concept of P versus NP. How many of you heard about P versus NP? If you are in computer science, like data science is a part of AI and computer science, you should know about P not equal to. And where is the best place to know P not equal to NP? You can go to my YouTube page. This is the course Introduction to, there are two courses, Introduction to Algorithm and then Algorithmic Lower Bound. In the Algorithmic Lower Bound, I have talking 2 sessions about P naught versus NP. It's a very good exercise, and you should be able to understand essentially what's going on. That is very important that you know about this. Also, we are talking about graph algorithms here. You can get the extended version of them at Introduction to Algorithms. We are talking a lot about graphs there. And as I mentioned about induction that we talked, also we talk about induction in that sense. So these are something that are available for you for free, and then you can just, use them to get the best coverage for these things. So please go and do that. So a linear programming is going somehow related to P versus NP. In some sense, lots of these problems, optimization problems, that generally they are hard. NP hard or NP complete the same thing, means that currently we don't have any polynomial time algorithms. NP doesn't mean non-polynomial, means non-deterministic polynomial. It's a positive sense. However, it is actually concept that so far practically means non-polynomial, because we don't have any polynomial time. When we talk about NP hard or NP complete. But so we have lots of optimization problems, lots of them, some of them we can solve in polynomial, some we cannot solve. The interesting thing is that linear programming in general, integer programming, you can solve all of these problems in a reasonable amount of time without going in details about a particular problem and know the best algorithm for that. You can get a very reasonable solution for that. And that is a very big advantage for it, because in practice you have the tools, and we will talk about it, Pulp, the software that you can go there and actually you can learn a lot about this. Good. So what is the objective? In any optimization problem, the objective is that either you want to minimize or maximize a linear objective. And I will describe what's the meaning of a linear objective. And these are subject to linear equalities and inequalities. Let's see an example. Say Max, imagine this person, he's in a pie eating contest that lasts 1 hour, 60 minutes. Each torte that he eats takes 2 minutes. Each pie, it takes 3 minutes. he received 4 points for each tort and 5 points for each fine. What should max it so to get the maximum points? First, is the problem clear? This is the problem that you want to solve. And here we are talking about programming. So this is important that linear programming is a programming. And as we will talk, there is some programming. This is the same as any other programming languages. You need to decide what are the variables. So variables are very important, and this is a type of programming. So the first question is that what are the variables? Or like we call it decision variables. So let X be the number of torts eaten by Max and Y be the number of pies eaten by Max. Good, just. Then the next step is that we need to determine the objective function. Objective function is the one that you try to minimize or maximize. For example, here we want to say there's a number of points. If X number of port, 4 points, and Y number of pi, 5 points. So you try to maximize Z, which is equal to 4x plus 5. This is your objective function. Then after that, the question is that some of the constraints that you have. These constraints generally, I mean, it can be, this is one type of constraint. You want to say that the time that Max spends, it should be at most 60 minutes. 2 minutes per port and 3 minutes per pi. Total should be at most 60. And we have these non-negativity constraints. Non-negativity constraint is something that happens essentially with linear programming. And it says that this variable should be greater than 0, or like X and Y, they should be both greater or equal to 0. And one important thing, so in the linear programming in general, we can have less than or equal, greater than or equal, or just equality. However, if you want to have just one language to do that, you don't need all three of them. Only you need this one, greater than or equal, or less than. Why? Because for the equality, you can just say that if this, you want to say this is like, I don't know, Z is equal to Y, you can just say Z is less than or equal to Y, and Z is greater than or equal to Y. That makes essentially Z and Y equal, correct? More than that, you don't need both of them. If you want to change this one, D less than or equal to Y, you can just multiply both sides by minus. So it would be minus D greater than or equal to minus Y. So in some sense, you can think about this is a language that you only have just greater than or equal, or just less than or equal. That's enough. And then, I mean, you have some of these conditions. And of course, this one, X greater than 0, is not anything different from this. Because again, you can just write minus of this greater than or equal to minus 60. Instead of all of them greater than this. And some of them are said that this variable should be non-negative. You can put it there, but the rest are regular constants. However, the languages that we are talking about here, you can actually have any of this one as objective function. But in general, you don't need it. You can always turn into 1.6. A feasible solution is the solution that satisfies all the constraints. So, for example, here, if we put X equal to 10 and Y equal to 10, of course, both of them are non-negative. But then 2 times X plus 3 times Y. 2 times X would be 20, 3 times Y would be 30. Of course, it's less than or equal to 60. So is a feasible solution. But it can be infeasible solution, or I mean, we will call it a solution. It's not a solution in some sense, but we can call it like essentially infeasible solution. So if you put it, X is equal to 10 and Y equal to 15, so it would be 20 plus 45, which is greater than 60. So that's called infeasible solution or infeasible assignment. An optimal solution is the best feasible solution. Among all feasible solutions, find the best solution. And here, for example, the optimal solution in this LP would be X is equal to 30 and Y equal to 0, if you can. In that case, essentially, you can see that's the best. how can we get it? Generally, I mean, if you want to solve this kind of linear programming with two variables, one way to solve by hand is that you will draw these constraints as some kind of lines, and you say that which way essentially you want to do it. And then you will bring the objective function down, and the first time that it intersects this one, depending to maximization, if it is maximization from the top, if minimization from the bottom, the first time that it crosses these things, that's the solution for this. You can do it by hand. If it is more than 2 dimensions, you may need to do some more tricks, maybe make it in essentially 2 variables. But in general, you can use this software that we are talking about, it Pulp, to solve it. And that's the thing that you should be very good at. So linear programming is a core. You can have a course on linear programming. You can have even advanced graduate course. Linear programming. And formulating the problem with linear programming is not always easy. You need to think about it, because this is actually a program that you write to solve a problem. And you might be able to write several ways, essentially, a solution for an LP. And sometimes one is more efficient than the other in terms of running time. And efficient means that if you want to solve this one using this software Pulp, then the running time would be much less. So you can actually spend a lot of time on linear programming, and that's a very important thing. You can read more about it. We are just giving some examples here, and you will see more examples in the assignments, but you can actually ask more in ChatGPT or YouTube about others. You will see more examples. I mean, hopefully in the future, I may have some courses on that, and for the future people, I can mention the places that they can see more examples. So here, the terminology is decision variables like X and Y. These are essentially the input to the problem in some sense. These are the quantities that you try to improve your objective function with them by changing them. These are some of the constraints. This is some of the limitation that exist on the decision variables. For example, this one or this ones should be non-negative, or this is the conditions. And last but not least is the objective function. Here is the one that you try to minimize or maximum. And it can have a different values essentially on different functions. It's like you can try to maximize rank, minimize cost, essentially maximize profit, etc. Lots of things you can essentially do it for this one. And you need to work on it such that you can get essentially the best understanding about this. I need to define a linear function. A linear function is essentially f is the one that it has f of x1, x2 to x, then is the c times x1, c2, x2 with some coefficient c1, can be positive or negative, plus some cn plus 1. You may have some constant here. So for example, this one, I don't know, plus 3. This is a linear function. It's quadratic if these ones are x1, some of them are x1 to the 2, for example. It is called quadratic. It is called integer linear program if we are have some additional constraint that this variable should be integer. So for everything that we have mentioned, it may become the case that the number of torts that Max, for example, try to do that, it becomes, I don't know, 20.5. And the number of pi that Max should eat becomes, I don't know, 10.5 or 10.7. That is the interesting thing about linear programming, the pros or cons in some sense, that the solutions are fractional. They cannot be like something like pi. They're always fractional solutions, but they may not be integer. Good. Great. Now, here, in general, so there are quadratic programming, and it is integer linear programming. We will talk about it more about them. But in general, a mathematical program is a linear program or LP if the object is a linear function and the constraints are linear equalities or inequalities. So for example, this is one condition or this is one condition. As I mentioned, equalities, you can always write it also in terms of inequalities. And then LP may have some non-negativity constraints. So you can do it equalities or inequalities. And so, as I mentioned, an integer linear program, integer program or an integer linear program is the one that it's a linear program. So all the conditions are linear still, but just one variable, you put this additional constraint that should be integer. So generally, you may write an LP, and you can assume, I mean, lots of the time, the variables, x, for example, I, should be between 1 and 0. That means that the variable between them essentially would be some number between 0 and 1. And it may become 0.2, for example. In integer solution, we will mention that xi should be either 0 or 1. Even for one variable, it is the case, it becomes integer program. So, what is the issue? So, what are the good things about LP? Linear programming actually is one of the, somehow in the largest set of problems, or like the most general problem that we can still solve it in polynomial. Polynomial time means fast algorithms. So LP, you can solve it in P. IP or QP. QP means quadratic programming. In the QP, you don't say that you don't need to say actually the variables should be integer anymore. It can be fraction. And actually, it can be like a CR root of 2, for example. Both these things are NP hard or NP complete. Good. What's the meaning of that? It means that for all practical purposes, I mean, they may take forever, essentially. Now, for the LP, there is a simplex method that runs in exponential time. That's a very, I mean, you can search for it. The code is not that hard. It's a good exercise actually to do it, to see how can you solve it. But in practice, in lots of the time, it's polynomial. It's a very fast algorithm, but in the worst case, it can be exponential. There is ellipsoid method that runs in n to the 6. N is the number of variables, decision variables, or max of number of variables and constraints. So in that case, it is polynomial, but it is n to the 6 is so large that it is completely impractical. However, it is more theoretical approach. I don't know any implementation of that. And n is actually the number of variables here. One important thing is that it can solve some problems, that the number of variables is polynomial, is n, but the number of constraints, it might be exponential. Theoretically, we can solve it using ellipsoid. But the one that is essentially the best one that we know is the interior point method that runs in the n to the 3.5. And this is the one that is implemented in lots of LP solvers. Good. As I mentioned, integer programming or IP and quadratic programming or QP, both of them are NP complete problems or NP hard. Again, go to the lecture algorithmic lower bounds and you will see NP hardness and NP completeness. You will see a very good idea. Good lectures, essentially. My best experience on teaching them on those lectures on YouTube. My YouTube at Hajiaghayi. So that's essentially like a crash course on LP, linear programming. I want to give you an example. How can we solve it essentially in Python using Python? So there are a few things that you need to So there are some solvers. So there is a Cplex. There is a Groovy. I think it is Groovy. You will search, and there is Pulp. These two are commercials, but if you want to for academic reason, actually you can do it for free. You need to get a license. Pulp is the one that is available as an essentially open source, and you can just use it. And it's very good actually. Now, Cplex and Groovy, these are some LP solvers. For them, they have like these constraints that you are giving. It might be the case, you should give it in a very particular format. For example, all of them should be greater than or equal these things. There is another thing, it's called AMPL. It was a language essentially to write some linear program. Why don't we just write it using Cplex or Ruby? Say here in this example that we had it, for example, the number of variables is 3. But say this is like a practical thing, for example, at Amazon or at like other sites that I have been there. So you try to maximize, this is something you want to set the prices of the items based on some constraints. You can actually use linear programming. How many items? You may easily, for example, have 3 million items. And there is some constraint on these 3 million items. You cannot write by hand all of them. You need to have a language. You know what are the conditions that you have it, but this LP, it will be generated by some programs itself. So in some sense, there is some core program that solves an LP. It is called LP solver. But there is also a language like Python or AMPL that you will write a LP, especially large LP in that. The good thing about Pulp is that Pulp is essentially both of them. You can just essentially write your program, your linear program, using Python commands. Good. So for example, if instead of, you can actually have an array of variables, and for example, you may say xn should be less than or equal to 0 for some n. So you can do all of these things because you are using the power of Python. You will see some examples here. So that's an important one. Ampel was like that for this, but now the interesting thing is also this. You can use Pulp to describe your program. And if you want to solve it maybe faster in some special cases, you want to use this one more commercial ones, you can actually say the engine of the solver. If you don't say anything, the engine would be Pulp. But if you can say that the engine can be Cplex or the engine can be Groovy. And then it's solved using that one, it might be fast. Good. Let's see some example of essentially how can we write some programs in Python, in Pulp, some linear program. Good. So here you can actually see a good example of this. So you need to know essentially basic linear programming Python with Pulp. So this is a linear program. This is an example. I don't want to go through that. This is very similar to the one that we have mentioned. These have two models of car A and car B, and these are some of the conditions that you have put it on those things. And then you have some constraints. I mean, I don't know why it's not there. There's some problem with the website. But there is the objective function, constraint 1, constraint 2, constraint 3, and constraint 4. Some of them are non-negative constraints. So it doesn't matter. Good. So how can we use Pulp to solve essentially this problem? So first you need to install Pulp. So you say pip install Pulp, and then you will, from Pulp, you will import everything. Now, you want to solve an instance of a linear program. So here, you say this is the problem. This is the LP problem. It is called car factory. And this is the LP maximize. It means that you are maximizing. So this is, as I mentioned, maximization, minimization, and you mentioned each one. Good. Now, what you say here, you will say that, what are the variables, the decision variable? You will say A is the LP variable car A. This is the name of it. The lower bound is 0. As I mentioned, there's some non-negativity constraints. What is the lower bound there? You can put upper bound, I believe, as well, but lower bound is enough as we discussed. The main thing is this one. The category is LP integer. Good. So this is the part that I have mentioned. Actually, quadratic programming and the integer linear programming, both of them are NP hard or NP complete. So you cannot solve in polynomials. However, in terms of programming, you don't have any issues here. You only need to say here in the polyp, you say this is an integer value. Good. In some sense, you can solve any NP complete problems if you can just formulate it as an integer linear program and just say that this variable should be integer. What is the, so then it means that we could solve NP complete problems easily. Is it the case? No. The issue is that as soon as you will put LP integer, then the running time can be much more. So you can do it, and that actually is doing some optimization for integer program. So it's not a naive thing. It's a good program, but integer linear program is not polynomially solvable at least so far. We believe that probably is not the case. So it means that if this happens, then the running time maybe takes forever. So as I mentioned, like for example, 2 million items you have, 3 million items you have. You try to minimize the prices, everything on them, it would be horrible, essentially. I mean, even grandchildren, they don't see the solution. If you don't put this one, then the solution would be fractional. What is the catch here? So the catch is this one. That, I mean, not all people know, I mean, maybe limited number of people know this one. The best way to solve a problem practically is that lots of the case, the solution should be integer. But what will happen in the real world? In real world, it happens that when you mention, if you don't mention the category is integer, it solves the problem. I had, for example, experience. So 10,000 variables, out of 10,000 variables, only 3 becomes non-integer, become fractional. No, for example, one of them becomes 7.2, the other one becomes 8.3, the other one becomes, I don't know, something like 8.8, say, and the other one becomes 11.5. All others are integer. So if it happens that when you solve this LP, all the variables are integer, actually that is the solution to the integer solution. Because when you say that something, when you add this additional constraint that should be integer, you are adding more constraints. So if the optimum solution to the LP without these constraints still is an integer, if you add this condition is also integer. So that's the optimum solution for the actual problem. Good. However, it might be the case that not all of them are like, again, 10,000 variables, only 3 non-integer. Only 3 non-integers. So in that case, you can round them actually. This 7.2, you can just turn it into 7. This 8.8, you can make it 9. This 11.5, you can randomize. You can do it 12. What will happen? This is in practice. In the worst case, it is not like that. But in practice, if you put LP integer and solve it, versus if you do it, don't put it, just say fractional and round it, the actual difference between that would be very minimal. I don't know, maybe not even 1%, not even 0.01%. So for all practical purposes, essentially you have this magic. You just write it as a program, as an integer program. Again, this is the one, if you work in the industry, you know this one, that for the real world problems, and the people are actually, still we don't know why, but lots of, as I mentioned, in the practical instances, generally the solutions are almost integer. Maybe 3 variables are not there, and these 3 you can just round it, and you don't lose that much. If you put it LP integer for 10,000, you don't get any solutions. But I mean, you don't care at the end of the day, essentially, because you can do it this one. So this is the magic that you have it with all. You can solve any problem, optimization problem. So somebody like your boss is coming, say, "Oh, can you solve?" I mean, this is the one problem. You just write it. You need to be good at formulating the problem as an integer linear program. I mean, in general, integer linear program and integer program, because we can have integer quadratic program. But these are all equivalent, all essentially NP hard. So you can turn it essentially one to other. The quadratic, essentially, when you put quadratic, also somehow it is, then you can, so I mentioned, if you say linear programming, then that is, you can solve in polynomial term. But when you say quadratic, actually, then it is equivalent of integer linear program, because both of them are NP completers. So you need to just formulate your problem as an integer linear problem, and then just use this pol to solve it. And even it is like fractional, don't say it is integer if it is, the solution should be integer. I mean, you can check that how much the difference would be that. But you see that the difference is not much, and those guys that become fractional, you just round it. It's called rounding. Yeah. So the condition, as I mentioned, if non-integer means that it can be, the number can be 8.7. But if you say integer, it cannot be 8.7. It can be, what was that? Yes, you have more constraints. It's harder problem, yes. But if you put that one, then it takes forever to solve it. If you don't put it, lots of the time, as I mentioned, for practical instances, it comes, the solution, the optimum solution actually is lots of variables are integers already. Few maybe non-integer, and you can run. Good. So that's the thing that you can do it. You can say category integer, or don't put anything, it would be fraction. Now, what about objective function? Now, you see, this is the variable, this is the decision variable. Here we have 2 variables. Actually, you can write a for, and then you design, I don't know, 10,000 variables, or 1 million, 2 million variables. Because you can just write a for. This is what you say. You put a for command essentially in the, like, for Python, and define, and this is the, also say that car 1, car 2, car 3, so on, because this is like, you can do any programming that you are doing with Python. Objective function. So for the objective function, you will say that this problem is the one that we define. You will say problem plus, to the problem, add this constraint as an objective function. Also the constraint, you see, you will say problem plus this one, a designer constraint. You will give the name to them essentially, and you will add these things. Again, you can write this one much more general than that by saying, I mean, because this is Python. So you can write in terms of 10,000, you can write a constraint that has 10,000 variables. Because you only need to generate these things essentially in Python. And then give some names. Good. So you will add to your LP, to your problem, you will add this constraint objective function on this, and then you will come here. Then it was actually car factory. You will say print car factory, or say, I mean, if you can just say car factory essentially, and print it for you. It says the maximization problem. that you want to maximize this subject to these constraints. And the variables that you have are non-negative variables. These are the things, and they should be integer because you mentioned that it should be integer. So that prints the thing solution for you. Then you can say, what is the status of that? Current status of the LP status of this problem, that status, it is not solved. You have not solved it. How can you solve it easily? Just say problem.solve. And you can say, for example, here, if you don't say that, is use the pulp, but you can say that use other solvers. And uses other solver to solve it. Like Cplex or Groovy or other thing that you need to install it. Then you will say print number of variables, then a.var value. What is the variable? What is the value of a after solving that in the objective function? It prints for you. Or total profit. This is the objective function. We can just essentially. And then it prints the things for you. Say the number of 1 for, like if you give essentially that other tort example, tort pi example, then that gives you the solution. And you know you can even print it, current status of that would be optimal. Find optimal. Sometimes we say that, okay, there is no optimal solution because not all the time you can optimize it. Like for example, if you say maximize X, and there is no conditions on X, then in this case, there is no solution because X would be infinity. It can also mention that, for example, there is no solution for that, or the solution is infinity. That you can do, or minus infinity. You can play with it. I mean, these are like some of the things. These are actually, this is some more examples that is interesting. You can use a linear programming to solve the famous Sudoku puzzle. How can you solve Sudoku problem using linear programming? In some sense, linear programming, as I mentioned, you can put equalities. So because you can solve equalities there, so you can, if you want to say 4x plus 5y is equal to 6, correct? You may have system of equations. This system of equations also you can solve it using LP. Why? Because this one you can just greater than or less than equal. Then you will just give it. And if there is no objective function, there is no need to say the objective function. If you just solve it, or say objective function is 1, it finds a feasible solution for you. And that would be the solution to the equation. So if you have a system of equations, so for example, Sudoku, you can write it as a system of equations and then give it to that such that it can solve. You can do, I mean, like amazing things with linear programming. It is essentially a language that you can solve anything with. And they use it in these companies and lots of things that you are seeing, essentially, they are using linear programming at the back end. Good. So you can read more about it and then see the links and more examples. But linear programming, I mean, you can spend, as I mentioned, a few classes even on that. But formulation, if you do it enough exercise, then you will be good at it. Reasonably good at it. Okay, so we talk about linear programming and pulp. That's a very important one, and you should work with it. Next thing that we want to talk about the graphs. Graphs are everywhere, like a road network, all Google Maps stuff. Internet, I mean, all connections are this one. Transition graphs, I mean, you can, any flow chart or anything. Social networks of this. All of them are graphs. And I mean, the graphs, they will call it essentially networks. That is maybe more industry name for it, essentially. But these are the same thing. Graphs are networks. You will know more about graphs. I will just, this is a very crash course on graphs, such that you know some ideas. Where can you find better, I mean, like a good set of materials? Go to my introduction to algorithm at YouTube. And then there is a very good set of lectures on graphs, different types of graph algorithms there. You should have a very good understanding about graphs by watching those videos. Good. But let's go, some very fast way. And then we talk about the concepts. Like we talk about, for example, probability theory, then we talk about this NP and stat things, essentially, that SciPy and NumPy, essentially, that we could solve lots of things. We talk about linear programming, we talk about the tools, poly. Here we talk about graphs, and then we talk about network X, essentially, that you can solve lots of problems here. In some sense, graphs and linear programming are very important tools. You can lots of graph problem, actually, you can write as a linear program, and linear programming you can write as a graph. So there is some relation between them. But sometimes if you essentially model the problem as the correct one or the closest one, you can get a solution, faster solution or more efficient solution, or like higher quality solution. So it's good to know both of them. So a graph is represented by two things, V and D. V is a set of nodes or vertices, like here, and E is the pair bars relation among V. So here, this is the edges we have. So we are for now talking about undirected graph. So the relation is symmetric. It means that if 1 and 2 is connected, 2 and 1 is connected. So it contains subsets of size 2. E is a set. So for example, this is the case. So in this case, V is equal to 1 to 8. And these are the set of edges. 1, 2. So it is a set of sets of size 2. Yeah.
So size 2 means that a segment only touches 2 nodes? Is that what that means?
Yes. It like means that this edge is connecting only 2 vertices.
So what would be an example of size 3?
Okay, so more than 2 would be essentially, they call it hyper edge. And this is the hypergraph. In hypergraph, actually the edges, you can say hypergraph of, like, for example, order K means that each edge can have up to K vertices. You can read more about them. Generally, for hypergraphs, you can turn into graphs of them. There is some reductions. You may lose some efficiency, but generally, hypergraphs also can be modeled like graphs. The general idea is that if you have a hypergraph between these 4 vertices, generally, so this is a hypergraph that contains all of them. You can model them by adding the edges here, all 4 edges here. Sometimes they can capture the one that the things, or hypergraphs are harder to solve the problems on them. So that's the thing, that if you can turn into graph, that's essentially you can have more efficient. The same thing that we discussed, essentially. You can write your program as a quadratic program or integer program. But if you write it as a linear program, then you have a better chance to solve it. You may lose something in the efficiency, like essentially in the solution, quality of the solution, but generally it's not much. The same thing here. So here we have just 1, 2 here, but in general, as I mentioned, you can have a hyper edge that it has more than 2 edges. In a directed graph, the same thing, just the edges are directed. So in this case, the directed edges are generally called arcs. So arcs, so we say nodes or vertices for the nodes. For edges, sometimes say edges, sometimes we say arc. But arc generally are more like the directed edges. Again, this is interchangeable. The people are using differently. So this relation is asymmetric. So you go from 1 to 2, for example. Here, in this case, E contains ordered pairs. For example, then we will write it essentially like this one, ordered pair, 1 to 2, 1 to 3, 3 to 2, and so on. The first one goes from 1 to 2, and so on. Abuse of notations. If the graph is undirected, sometimes they are using essentially ij for that. Just also is ij. But in this case, if it is an unordered pair, essentially it means that if ij belongs to the graph, ji also belongs to it. So for example, you may see this graph, they may write it like this instead of writing in terms of sets. So you may see it even for undirected graphs. Okay, so the graphs, lots of graphs, again, the same story. Undirected graphs, generally, you can solve the problems easier with them. than directed graphs. However, lots of practical problems are actually directed. For example, social network, lots of social network, right? For example, LinkedIn, I remember, or Facebook, these are more like the undirected. If you are a friend of a person, that person is a friend of you. LinkedIn was like that, but then lots of this Twitter, Instagram and other, this concept of followers came. But then when the follower came, then becomes more directed. You connect, you follow someone, but that person does not follow. Transition graph flowchart generally are directed. Road networks can be directed or undirected. So if generally, in general, you can say directed, but as I mentioned, if you can manage to do it undirected, generally you have a better solution for it. And road network, yes, you can say that this road, it is directed this way and this way, but you can, instead of between these 2 points, but if you can both roads, they can use it, you can just put it maybe just one undirected edge, because both ways the people can. Internet also you can say directed or undirected. Like maybe you can approximate it with undirected, but it's not quite that. For example, if you have a cable companies, cable internet at home, they say that your download speed is 300 megabit per second, but your upload is maybe 20 megabit per second. Some companies may say, like I think Verizon was searching and say that we have the same upload and download speed. So if you have a different upload or download speed, then you have a different essentially. You can have it. You can consider it directed edge. Good. How can we represent a graph? So one way is to do it is via adjacency matrix. What is the adjacency matrix? This is essentially the array that any two vertices, if there is one to one, this is called loop essentially. Generally, we don't have loop. If 1 and 1 is not connected, then it is 0. If 1 and 2 is connected, you will put it 1. And if it is an undirected graph, this matrix is symmetric. See, it is symmetric. Another way is to use the linked list. Linked list says, okay, the one, and you can, of course, you can have a list, you can have a linked list, you can have double linked list, all of them. You can do it in C++ or you can do it in Python. Both of them are available, so you can use them essentially to do this. So you will say that 1 is connected to 2 and 3. So 2 and 3 is 2 is connected to 1, 3, 4, 5, and so on and so forth. So for each vertex, there is a linked list containing all neighbors of it. When the graph is aesthetic means that you don't want to change the graph. Actually, you can use this type of array of variant lengths for the essentially list and array are the same almost in Python. But in C++, you can also have a vector, and then you can have the size of that. It can be, it can be different essentially. You can have this type of things, array of different things. So that would be more efficient because you don't need to keep this pointer. Pointer also takes some space. So assuming that we are dealing with an undirected graph, say n is the number of vertices, m is the number of edges, and say m is between this. dv is the number of neighbors of v. Good. So we had two ways essentially, the representation of the graph as adjacency list or adjacency lists, adjacency matrix or adjacency lists. How many of you are familiar with the concept of order? It's O of something. O of n squared. Okay, where can you learn about it if you don't know? Go to Introduction to Algorithms. I have a good class fully dedicated to order. Like induction, you can see it, and then talking about order. You should know about order. You cannot work in the computer science or essentially like data science and you don't know what is order. Essentially, when we say that order n means that some c times n or some c that we just removed, some constant that we removed. That's a general concept, but please go there and you will see different concept of order there. So when we don't want to talk about which constant is that, because this constant somehow is dependent to the computer, the speed of that, lot of other things. We don't care about it. We just say what is the in terms of variable. We say order. That's a very short thing, but you should go through that and you will understand better about that. Now, I just want to give you some idea that which one of them we should use it. So m, the number of vertices, is at most n minus 1. If the graph is connected, it should have at least n minus 1 edges. The number of edges should be at least n minus 1. N is the number of vertices. And this would be a tree, essentially, a graph that does not have any cycle. You should go and then just go to Introduction to Algorithms. And then there are lots of things about trees, properties of them. You become very familiar with the concept of graph. There, you can do that. The maximum number of edges in an undirected graph is n choose 2. How many of you are familiar with this? N choose 2? Okay. N choose 2, that is something that you should know about from the high school, actually. If you don't know that, I mean, we are talking in Introduction to Algorithm a little bit about it, but it's the more basic stuff. You should just go on n choose 2. But n choose 2 actually would be n times n minus 1 over 2. And you can read a lot about it. This is more basic combinatorics. And this is like, here we have 250 course that is talking about it. But just n choose 2 or n choose k, read it at Wikipedia. And n choose 2 essentially means all possible pairs. So the maximum number of vertices would be this. dv, as I mentioned, the number of vertex v. So how much the memory usage? If you want to use a matrix, the memory usage would be n squared. Why? Here, you see you have n here, n and n. So an array of size n by n would be n squared. Again, the constant, we don't care about it, like 0, 1. What about in the adjacency list? If you want to represent it in an adjacency list or this kind of variant length array, then for each edge, so if you have edge I to j, for I, you will mention j, and for I, you will say j, and for j, you will say I. So each edge appears twice, a space that it uses. So it would be 2 times m, the space. But order of 2m is equal to order of m, because we don't talk about constants here. Or we don't care about constants. So here, the memory usage would be n squared versus m. So as I mentioned, m can be, also we have these graphs. If the graph, we have a sparse graph. And we have dense graphs. Dense graph, when the number of edges, m, is order n to the 1 plus epsilon. This one, on the sparse graph, generally we say O tilde n. O tilde means n times polylog, essentially. So a dense graph is the one that the number of edges are more than linear than the number of vertices. A little bit, the power is n plus some constant. Otherwise, it would be a sparse graph, which is order n. Lots of practical cases or lots of social networks, etc. We have a sparse graph. A sparse graph, in this case, if you use the linked list, then it would be m with order n, so it would be order n. So this is much better than this. And if you see, for example, this is the reason that, for example, if you go to Facebook, you say that you can have at most 5,000 friends. Or, for example, Instagram, you can follow at most, I don't know, 2,000 people. These are all constraints that these people are putting there because they want to have a sparse graph. And if they don't put it, of course, I mean, you may not be able to add 10,000 friends, but you can write a program to do that. And then essentially you can destroy make their program very inefficient. That's the thing that they don't allow that essentially this is. So here, this is essentially this one. So you really want more sparse graph, and lots of practical ones are a sparse graph. So for a sparse graph, linked list is better. There are some dense graph, but generally for dense graph, so for example, just think about it that for Facebook, there are, say, 2.5 billion people. If you want to have an array of 2.5 billion to the 2.5 billion is times 2.5 billion is a huge thing. However, if the number of, I mean, each person can have at most 5,000 friends, then it would be 5,000 times 2.5 billion, which is not a very large number. I mean, it's large, but they can control it. So then, of course, I mean, then existing that linked list is a very good thing. Why don't we just always use linked list? The issue is this one. If you want to check an edge UV exists in the graph, in the matrix one, you just go there. You want to say between I and J, there is an edge. You will go to the A of ij and see whether it is 1 or 0. So that is order 1. It's just constant. However, if you want to do it with linked list, then it would be the degree of du. Why? Because you need to go to that linked list and you will check whether with linked list for you whether v appears or not. That is the distance. If you want to list all neighbors of v, then this is bad. Because why? Because you need to go essentially in the row I and say what are the vertices for them that this adjacency matrix is 1. All of them you will list it, but that is order n. However, if you want to do it in the list, all of them in the essentially in the adjacency list is very easy because you will go there. So in general, if I thought that this is also interesting. So when we, for example, when we talk about follower, there we talk about the directed graphs, correct? We have two concepts. We have the essentially a vertex in directed graphs. We will call it in degree and out degree. So out degree means essentially, let me just, so out degree and in degree. So let me change this one. So this is U, this is V. If you have edge from U to V, this edge comes to toward out degree of U and comes towards in degree of V. Good. So in directed graph, we have in degree versus out degree. However, to make sure that the graph is sparse, it has order n edges, you don't need to essentially bound both in degree and out degree. As long as you will bound the out degree, then you can make sure that the whole graph has a linear number of edges. How come? Like you see in the Instagram, one person can be followed by, I don't know, billions of people, or Twitter, I don't know, who has the most number of followers, probably I think Elon Musk, or he was like second or third at some point, but maybe now he's the number 1 in Twitter. The person who follows them. So in degree of Elon Musk is a lot, but out degree is a small essentially. Because you can follow, for example, in Instagram only 2,000 people. As long as you have this condition that essentially the out degree is at most 2,000, then you can make sure that the total number of edges in the graph, it would be at most 2,000 times n. Because each edge you will consider it appears as in degree of one vertex. And the in degree of each vertex is at most 2000. So we have n vertex times in degree of that, which is at most 2000, would be n times 2000, which would be order n. You need to be very familiar with the order. And again, please go and watch those videos about the in the introduction to algorithms about the order and graphs. That would be very important. And graph algorithms. This is just some basic about this. One important problem that we have is essentially, there are some important problems, like connectivity problem. Whether the graph that is given to you, whether this is the graph that is given to you, whether S and T are connected or not. It means that whether there is a path between S and T in this graph. This is very important. For example, like, a basic thing is that like at the Google map, you will say that I want to go from here to Europe by car. Then say it is impossible because it's not connected. And sometimes I think maybe give sometimes the options that you can take a ferry or something like this with the car as well. But otherwise it's not connected. So that's a very basic problem essentially. And the other one is the shortest path. You want to find the shortest path. It is essentially Google Map that finds the shortest path. And these are all algorithms essentially. Two things essentially there are here. It is depth first search and breadth first search and depth first search. These are two basic algorithms that you should know about it. Again, go to introduction to algorithm. I'm talking exactly about both of this. These are like very basic algorithm that you should know about it. And these are some of these, for example, P versus NP or BFS versus DFS. These are becoming actually more philosophical things. For example, BFS, when you say that I want to do BFS, it means that you will just essentially go all the breadth and layer by layer you will go. Depth first search is that you will go and find something and you will go essentially deep to see whether you can find it or not. So it is essentially you are doing more in-depth things, like, or you are just doing it essentially in the breadth level. And these are some philosophical things that you can understand. This is beyond that. Like the same thing versus, for example, for P versus NP. So as I mentioned, so NP means non-deterministic. Non-deterministic polynomial. What's the meaning of that? P means solving the problem in polynomial time. In the total running time should be polynomial. NP is a positive thing. Again, we are currently using in like NP complete or NP hard, we are using it in negative terms, a non-polynomial for practical purposes. But the actual thing is a positive thing. Non-deterministic polynomial. What's the meaning of that? The whole meaning of NP is this one, that if somebody gives you a solution, you can check in polynomial time whether this solution is a valid solution or not. NP is a set of problems for which if somebody gives you a solution, you can check whether this is a valid solution or not. This is a positive thing. So this is, again, what is the philosophical question? This is the philosophical question. So it is. This is essentially, we don't know whether P is equal to NP or not. This is the probably most important problem in computer science, and maybe in the world actually at the moment, because computer science is almost everywhere, and AI plus computer science, I will say, the same essentially. So what is this question? Philosophical question is this one. So there is a person. This person, it can distinguish a good art from bad art. I will say this is a good art by a famous artist. No, this is, you draw it. It was not a good one. And again, it's a very hard one. Sometimes you will say Picasso or others, he had just 2 lines, and these 2 lines, they will sell it, I don't know, for a very big amount of dollars. Okay, just 2 lines, I can write. Even my child can write 2 lines, crossing lines. But say this is by Picasso. That's very big meaning for that. But anyhow, so what's the meaning of the P versus NP? The question of P versus NP is that if the person can distinguish a good art from bad art, or from a famous artist versus non-famous artist, whether this person is a good artist himself or herself or not. That's exactly the question that we have. So here we can say in polynomial time, we say that this is a solution for the problem or not. We say that can we obtain that solution if it is the correct one or not? We don't know. So in some sense, this is a philosophical question, P versus NP, whether if you can distinguish between good art and bad art, are you a good artist or not? We don't know the answer, at least for this P versus NP. But anyhow, these are some basic ones that you need to know about it, and you need to understand it from the heart, essentially, not just read it, because there are important meaning for them, essentially. And you cannot work on data science if you don't know this basics. And you have courses later that you have it. But if you go to my courses, they are generally, I mean, very comprehensive. You should be able to get it in introduction algorithm. Very good ideas about this that can be used for other courses. Another thing is the bipartite graph that use essentially a lot. A graph G is bipartite graph. If the set of V can be partitioned, partitions mean that you can essentially, you can do it. V can be written as L union R such that L intersection R is empty set. This is called partition. I can write it as a left and right such that if you see this is a bipartite graph, there is no edges here between L and no edges between R. All the edges are between L and R. These are very practical graphs. Almost you will see it in any marketplace is like that, essentially. If you go, there is a one potentials of e-commerce video that we have. We talk about marketplaces. That's a very good one, actually, too. This is not from the course. It is another video that is there. That is interesting one to know about it. What's the meaning of marketplace? Generally, for example, consider Amazon. In the Amazon, we have sellers, we have shoppers here, and we have sellers. Good. Generally, I mean, for lots of things, is a valid thing. So that there is no edges between, or we don't care about the edges between shoppers or the edges between sellers. We only care the edges between whether this shopper wants to buy from the seller or not. Another thing, for example, this is, you may think about this as the advertisement slots, ad slots versus advertisers. So here, advertisers might be interested in some ad slots, on display ad, for example. And this ad slots, might be liked by some of these advertisers. And each advertiser may be interested in several ads. That's the thing that we care. We don't care that much the edges between ad slots or the edges between advertisers. Another example, so these are big industries that I'm talking about. This advertisement is $1 trillion industry. All of them are based on this graph, and understanding this graph the best. Another very important thing that you are using it. At Uber, these are essentially riders versus drivers. Good, riders versus drivers. The same story again. You don't care that much maybe about riders and drivers. You say who is rider and who is driver. You want to give, who can give the right to this. These graphs are, all of them are based on the, if you go to any of these big companies, they have generally marketplace division. Marketplace division is just talking about this bipartite graph, properties of this. Good. And good. One other thing is also important. For each edge or each, for each vertex or each edge, we may have lots of properties as well. For example, for an edge between two vertices, we want to say what is the distance between these two guys, like for the thing, or whether this guy likes these things or not. Or for advertisers, for example, how much this advertiser can pay for this ad slots. All of them, you can, this is the property of this edge. And of course, each vertex also has some properties, like who is this advertiser? What is the idea of that? What are the budget of this? All of this. And these are some of the things that we can represent it in database. We will talk about some of them later. Good. So these are the graphs. You should know more about the graphs. These are everything. And you should, this is again, some mathematical concept that you should improve your thing. This is like linear programming. You should be able to consider the problems and see which graph problems is the one that is closest to your needs. Because if you know that, then you can use Network X library. It has essentially the Python package for creations and manipulation and study of the structure dynamic of complex networks, means graphs, essentially. It has data structures. It has essentially lots of graph algorithms. If you know this problem that you have is actually this particular problem, the name of this problem, you can search, of course. One easy way is that you can give the description of your problem to ChatGPT and say, this is closest to which program, which graph problem. It probably can hint you to the corresponding problems. Then you will go and read it. Oh, so this my problem is very close to this problem. Then you will go give this graph to Network X. There's a good implementation of the problems there. You will go there and you just run and use this package to get the implementation. You will solve your problem. So that's the practical way to do that. You can actually draw the graph, have a nice thing for drawing the graph. It is important. Well tested with over 90% of code coverage. It means that 90, still there might be some bugs in some of this algorithm because some of them are complicated algorithms. But 90% of the code is, tested. Maybe it's more essentially this one. So let's go to this one and see a little bit about this, about Network X. Recording. Great. Okay, so this is Network X. This is great things essentially to work with. Here, as I mentioned, it says that essentially 90% of the code is like checked. And let me say this is the introduction to so documentations. So good. Okay, so this is the introduction about a Network X essentially. As you will see, you can do lots of things. This is the basic thing. How can you install it? Just say import this network as NX. Then you can have a graph. So this is a graph. Digraph means directed graph. Multigraph. Multigraph, it means that between two vertices, you may have more than one edges. Or then sometimes you have a loop. And this can be multigraph or directed multigraph. So that means multi-digraph. You can just mention that nx.graph, nx is this one. You will just define G as like that. And then these are the nodes and the edges. So you can have nodes and edges that I mentioned. So if you want to have a graph, you want to add edge. So you will say G is the graph, the undirected graph, add the edge 1, 2. For each edge, you can say also the weight. As I mentioned, the edges may have some property, like weight means length or anything. We'll say weight of that would be 0.9. Good. Okay. So that's about this one. So you can say essentially the weight of that. You will add the edge. This you will add. You can actually add edge. You can say you can give some add attributes. Can be anything. You will say add edge x y to x, and the function on that is a math cosine essentially. You can have complicated things essentially, and then you may give it essentially as a list. And then instead of adding one by one, you may just read this list from the input, and you will just say add edges from the list. It adds all of them. You will read from a file and then add everything. Or you may the list also may have the weight essentially, and that adds all of them to that. Good. So these are the weights and others. You may also have it. So if you want to draw essentially some kind of random graph, especially this Erdos-Renyi graph, that each edge will be with probability p in the graph, you can generate using that. Or binomial graph is another random graph that you can generate. All of these are there essentially. Graph reporting. If you want to essentially do that, I mean, you can just say what are the so for example, this is so you can have things like this. You may have a for say for E in the list of G edges. List of G edges means all the edges, and then for each edge you may essentially iterate. You want to do anything essentially. This is the interesting thing. So you can have this graph, NX graph. This is the graph with the edge weight, or here edge weight are just the distances between the vertices. And then you will say that all the edges from E you will add it to your graph. And then you will say use the Dijkstra path. Dijkstra algorithm is one of the shortest path algorithm. That's actually the one that is used by Google for Google Maps. Of course, they are doing, I mean, adjusted essentially for their thing. But the basic thing is this. And you can actually know more about it again. Introduction to algorithm, we talk about the Dijkstra algorithm, everything about it. You will learn both from orders and math and everything there. There, and what do you say? You say the Dijkstra path. Find Dijkstra path, find the shortest path between A and B. Here you say that print the NX Dijkstra path G in the graph G from A to D. From A to D, it reduces the shortest path. So essentially, if you give the Google map to that, this one is not that efficient. I mean, like you need to do it more distributed way. But a large graph, when you can give it to that, and then you will say find the shortest path. Actually, it can give you the Google Maps solution. You can also draw them. This is also important if you want to. So you may consider this one. This is a typical thing. So you say that I have a graph G. It is a cubical graph. I mean, this is some graph, cubical graph. And then you can have it a matplot, pyplot, PLT. This is very important. Matplot is the one that we can use it. We will talk more about it, but this is the one that you can actually draw anything there. So you will you will define this one as a subplot, and then you will draw this graph. And then you will add this subplot to this one, and then you will draw essentially the whole thing. You can say what are the edge colors, what are the layout, everything. You will say circular, for example, or any other things. So you can draw the graph very nicely using this one. All of this, I mean, if you want to implement it yourself, it takes a lot of time. And there are I mean, this is like the research area that I'm working. All of this, the people work little by little that, I mean, improve, for example, the best way that they can draw a graph. And the people are doing research, publishing papers, and the best of them in some sense, so far, the best that can be implemented is implemented here. You just use them essentially. All the science, you have it at your disposal. This is the data structure. For example, you can, as I mentioned, you can show this one as a, like you can say as adjacency matrix or as an adjacency list. You can do both of them, all of them essentially. So you can download this page as a Python code. I think you can just go and just use it. There are different algorithms in these things. As I mentioned, these are the different problems. These are very, for the graphs that people consider, I don't know, for a large line, like Euler graph. You may heard about this Euler graph essentially. Or Euler. This is like for a long time the mathematician considered it. And these are some famous problems that say that these are very important or fundamental problems on graphs. The people have defined them. And then for you, if you find a problem that you want to say, oh, this is a network problem, I need to see that. As I mentioned, you can give it to ChatGPT, say, this is closer to which problem. Then it gives you one of these problems and go and read about these problems, like Wikipedia or even ChatGPT, we can get more details about them. And they say, oh, this problem that I have, it is this problem. Then you will come here, use this algorithm, and you will just give the input graph. You can have a file, read from the file. That you should say, how should you read from a file? Go to ChatGPT and say, how can I read a file in Python? Give you the things. You will open it and then it will read for you, but give you the code. So you will get it, then you will use this algorithm, say, run this algorithm, get the solution. You have the solution. Beautiful way of getting the solution. So here, there are lots of things that I don't want to go there. And what else? So this has... it's talking about the different drawing, the randomness, exceptions, what are the things, and lots of other things. Reading and writing graphs, like essentially how you can read or write from the file, etc. It's talking about it. Yeah, so you should go and learn more about it. Just go here, try a different algorithm, and you become actually very familiar with these concepts. Great. Okay, so we talk about Network X, and this is another great tool that you can use it. Like lots of science has been done such that you have such a tool essentially. So we talk about some basic technology, stack and best practices already. Of course, we talk about Pulp and Network X, but there are some more things. So Python, Jupyter notebooks, we already talked about it, and this is a collab things that we talk about it. Let's talk about a few other things, GitHubs, cloud computing, and containers, or Docker, essentially. So the first thing is the version control. So like when you write essentially programs, you want to have some ideas about the versions, the different versions of the program. You want to have the history of them. You want to be able to collaborate with others. The people can write the code. That happens a lot in big companies. They use essentially, for example, Jupyter Notebook or others, but you need to have some kind of version control system as well. And you want to make sure that if you want to change lots of places in the things, you don't essentially ruin the previous program. You should have things to do that. So there are, you can always change the folders and have the folders and change it. But there are some issues with that. By the way, one of the best approach essentially to have it, for example, is that if you have your main things is main.py, you want to have a next version of that, you can just save as this one as the main1.py. Then again, save as main.py. So this is like, in this way, you will save as this one as main one. You will have a copy, and then again, you can save as. Of course, you can close it and open it again, but you can just save as this one. This way, you will have a copy of this as main1.python. At the same time, your main file, your most up-to-date file still would be main. If you want, next time you will change more, you can again save it as a main 2.py, and then again save as main.py. So this way you have another copy of that. So you have a history of that. That's actually a good way to, I use it essentially if I have a different version of the program. And the good thing is that you don't need to change all of your programs if you want to do it on the web, if you want to essentially use it, Dockerize it or anything. Always you are just talking about main.py py or any other version without any number in it. But at the same time, you know that the latest version of your file, if you lost it, it is main 20 is the one. So main 20 is the latest version that we have. So this is one way you can do it. Also, you can do it using a Dropbox. Dropbox is very good in tracking all the changes in the programs. I mean, this is mentioned more for the name folder approach. I mean, this is the way that I have mentioned actually is resolve some of these issues. But still, I mean, it can be hard to track. This is not a bad way, but if you put it like this way, it might be hard. It is memory intensive in a sense that each time you are saving the whole file essentially, and can be a lot of things essentially. Probably the Python file is not that big, but if it's some databases or something like this that you want to big file, then it can be an issue. It can be slow because the files can be large. It is hard to share. This is the issue essentially. It would be hard if you want several people are doing it. And no record of authorship. Of course, that you can also, on the top of the file, you can say it is written by whom, but if different part of the thing is written by different part, it would be hard. Lots of things actually will be resolved by Dropbox, for example. And how many of you use Box? Or you heard Box? How many of you use Dropbox? Okay. So Dropbox is a very good one. I mean, Box is another one, but not used that much. I think UMD is using it, but we are not using that much of that. But Dropbox is a good one, actually. And the good thing about Dropbox, it was better before with the free version. You could go back to all, like from now, you want to go, what was the version of this file 6 months ago? You could go all the way to 6 months ago, and it gives you essentially what was the version at that particular time. And what is the idea? The idea here is that, so here, when I do main 1, main 2, etc., I will keep essentially save the whole file. But the idea is that you don't need to keep the whole file. This is the programs that are written by the people. People change slowly the files. So you only need to essentially keep track of the differences between two versions. And this difference is done by whom? That's the whole idea, essentially. And this is the way that they are doing it, at which time this has been done. And you can actually create a graph of them at any time you want to go back and see what was the version at that. This is just some graph problem, essentially, that you can solve network problem. That's the way that they have done it. But I mean, the current thing I have seen more recently, Dropbox, is if it is a free version, you can go only 1 month back or something like this. You cannot go all the way back, essentially. And this is something, I mean, the free version maybe is not the best. A Google Drive is another one that you can use it as well. I mean, that is, yeah, this is still has a problem. If it's a very large folder, you will upload it. I mean, you can sync it. I didn't use the sync of Google Drive that much. It was not that easy. But even when you can have a copy essentially at Google. But when you do it, it is a large directory, lots of files. If you try to download it, it may not download all the files. The good thing is that it has all the files there. So, but if you do it from one computer, put it there and then get it back, you may not have all the versions. But the only thing is that I always know that, okay, if there is some version is not there, I had it, I should just go and then Google Drive. Then individually you can download that. But anyhow, this is one of the things. Generally, we have this kind of centralized version control. This is a central party that you will put everything there. And then what is the idea? The idea is that the collaborators, they are pushing their things. And then any commit that is done, I mean, after the push, should be compatible with the other one. Otherwise, it should be solved manually. And the examples of this are CVS, SVN. SVN is a new version of CVS, and Perforce, that is another commercial one that is used. But the distributed version of control systems are more essentially like used nowadays. Here, there is no central repository. every repository has every commit that exists. And essentially, you have lots of copies of that. And a good example of that is Git. So all the changes, I mean, the developers are doing that. This is the, so in the central base, everything is here. And in a distributed version, I mean, these are like the different versions that they have it. And this is a more complicated system, but still you can do all of these things. The catch is that like the central also by now, for example, you may do it in the Dropbox. You may think about the Dropbox as a central way. But in a sense, Dropbox itself is on cloud, and anything is in the cloud is a distributed. So maybe this is central way anyhow is also a distributed way. Not a big difference. The only thing is that Git maybe is the newer version that the people are using. So Git is a distributed version control system developed as a repository system for both local and remote changes. You can have a teammates to work simultaneously on the files. You can track each commit, and you can give a detailed documentation about it. And it allows for advanced merging and branching. This is especially important. Like, for example, you have a master, essentially, branch. From this one, you get some branch. So this is a master. From you will get essentially a copy of this. Then in this branch, you will do all your changes without others essentially noticing, because the others also work on their things. But at some point, this is the thing that you want to essentially put it such that everyone is using it. This branch, then you can merge this branch and the master. And then all these changes will be essentially essentially distributed to all other people that who are using it. So this is a very beautiful way of doing that. It's more complicated. So as I mentioned, these things essentially become more complicated, such that you can do more complicated stuff with this kind of control things. So the idea that, I mean, you want someone else essentially is host for you for this one, such that you have a copy there. Git is a general distributed version control system. There are several versions. GitHubs, Bitbucket, GitLab, especially GitHubs and Bitbucket are the most famous ones. GitHub, I mean, lots of famous things was done, essentially. Python, Bootstrap, Angular, Django, Visual Studio, all of them are done essentially. And some very nice project has been done. There are some reason to use the others, especially Bitbucket. There are lots of companies actually using Bitbucket. Bitbucket is somehow like supported by Atlassian. Atlassian is, there are two, Atlassian, I think. You can search Atlassian. So this is, there are two software companies, famous ones. This is Salesforce and Atlassian. Also, there is Microsoft, but Microsoft has its own stuff. Sometimes it's doing essential things. In particular, GitHub is now owned by Microsoft. But at the same time, Bitbucket, it is Atlassian and Salesforce. These are two important companies that they develop. Like, for example, you come to the university, say, okay, you need admission system. You need, I don't know, some way essentially for faculty reports or something like this. They will come and create this software for you essentially. And these are like the big companies, both of them, both Atlassian and Salesforce, as I mentioned. But again, this GitHub also is supported by Microsoft, which is also somehow a software company. They have their own things. The Bitbucket, I mean, it's used with lots of, I mean, company. Again, if you want to get it more commercial way, you need to pay essentially. I think $20 a month or something. You can get a reasonable version of it. But there are some good things about this. So let me just do this. Show some of this, but yeah. So, but before doing that, let's talk about the social coding. So this concept of essentially GitHubs essentially create social networks about the coders. So this is John Dickerson, actually, the assistant professor here. Some versions of this slide first it was prepared by him, and then Professor Amal Deshpande, and then I have changed more essentially. So these are some of the things that you can essentially see about him, that how many things stars, etc. So this is some out of the coding, and this one, the social coding is coming, social networks are coming. So these are some of the important things about the Git commands. So Git is essentially, there are two ways to do that. One, you can go to Bitbucket and do that, and I will show you how you can do it on the website. Other than that is that, I mean, you get essentially this, there's a repository there. You will essentially get a clone of that things, or you can initiate yourself for the first time, or you can get that clone. You will get that clone here, and then you can do the changes. These are the most important one, essentially, the Git pull. So anything that you want to do, anytime that you want to do the changes, always you should get Git pull, because that's the all latest version of the thing changed by others, you will get it. Add, essentially, if you add a new file, you can add essentially this new file. Or if you want to remove some other files and you don't want to use it, then you just say git add -u that removed it. Then the other one is git commit. Git commit /m. Say that, okay, I have this one. You will add all the files that you have changed it, and then you want to, like if you add one file, you don't need to add it again, but it's a new file you need to add. Then you will say git commit. Git commit, it gives a name for the changes that you have done. You describe that what you have done, this is documentation that you have. And then nothing is done until you do git push. When you do git push, then this will go essentially to that one and will update it. And essentially, this is a good example. You can make a repository on the GitHubs and clone it on your machine, or you can do it actually in the Bitbucket. And I would say both of them you should try, but Bitbucket maybe is easier actually to work with. Let me go and check these Bitbucket things. Good. Okay, so for example, this is my Bitbucket. You can log in, essentially create using your Gmail or others. And then here you have the master things. And then in the master, you have a different file, essentially. And if you click on, so these are the files that you have in the directory. You always have the copy, and this is a LaTeX file. So there you will go there, you will see the LaTeX file. If you want, actually, you can edit it here, and then you will full commit, essentially. You put the commit. So everything you can do it from the website. Or you can use it the git commands. So this Bitbucket is essentially is compatible with the git commands. So this is the version that you can create it. And then you can do checkout, for example. It gives you the address if you want to make a clone, etc. Here, you can go there and then do this. Good. So this is the one you can actually go and create this one. And this is the project. You can have different projects here. So for example, this is the all project that I have it in the master or other stuff, books, this and others. So that's one thing that you can do it. Then there are also other stuff that you can do it here. So here, if you go there, I mean, there is a link that I have put it there in the PowerPoint. You can actually do a lot of stuff here. These are some basic Git commands from Bitbucket. These are I just mentioned. So you can essentially, you can get the config file, what is the email address, etc. Add a user that they can update the files, etc. You can create a local repository, but Git in it. Or you can clone it from some path, essentially, that you will get it from Bitbucket, for example. Then you can check out the latest version. So this is like the checkout, essentially. You get the latest version of that, the file that you want to do the changes. You will go to a company, say, okay, you want to start changing the program, you will get this one. If you want to add files, essentially add one or more files to the indexing, such that it essentially keep the keep tracking of the changes, you will do that. The commit essentially, you see, to remote repository. So if you do the commit is doing these things essentially for your local repository and do the changes, but it is not done until you will push it, essentially. Push is the one that is essentially sends all the changes there. You can say get the status out of that. This is, I mean, So you can see what are the remote repository, maybe there are several of them. And these are the branches. This is the branch that I have mentioned. This is very important. You will create your own branch, you will do all the changes. And then after that, you can merge actually this branch with the original one, such that everyone is using the new version of the files that you have it. Of course, this should be done after all testing all the components, etc. You can git push origin, essentially put the branch to your remote repository and other things. You can merge essentially two branches, etc. So these are some of the things that you can do there, and these are the good things at Bitbucket. You can go and test this and read more about them. And if you want to, test essentially, you can also try more of them with ChatGPT also. Just ask for it and then just talk about the git commands and give you the things essentially. So good. Okay, so we talk about this one, GitHubs. And GitHubs, essentially, all these GitHubs distributed ways based on the concept of cloud computing. So we talk about, clouds before, and but here I have a bit more formal things about it. So essentially, cloud computing based on the fact that you may buy a computer, the computer is doing compute things for you. But you may consider this is a product that you buy. But you may think about it computing as a service that somebody provides for you. They have a computer and then you can rent that computer. So here, everything happens in the cloud, both storage and computing. These are the two important things. You will store everything or do the compute things. And one example of that, for example, is the Google. So at Google, you can Google Drive, you can save the stuff. At the Google Colab, you can actually write even the programs and get the compute resources. And so here, all these personal devices, laptops, tablets, everything, they can just interact with the cloud. What are the advantages? The advantages is that, you can go from one device to another device, essentially. That if you read the person who, actually the founder of Dropbox, that was the whole idea. That I want to, was a student at MIT, so that I had something at my university, something at lab, and then I wanted to have the most up-to-date thing. That was the whole idea to create this essentially. And Dropbox is a cloud as well. Lots of things are cloud essentially. So you want to have like efficiency and especially scalability. For example, you are writing some programs using some web site essentially, such that the people can come. Now you can put it at the Google App Engine, and Google App Engine, you will see that if there are 10 things, 10 users, then I can just do it. But if there are 10,000 users, then it adds more apps, copy of that, if you have written it correctly, that they can work with their databases. And essentially, it makes it very scalable. So you can present your things for not only 10 people, but for 10,000. How if you don't have it, then these 10,000 people, their whole traffic, everything, you should handle it yourself, which is not an easy thing. But then you can do it scalable. The reliability goes up again because it is done by someone else. As I mentioned before, like Microsoft, there was some videos that I was watching. Some of their servers, they will put it under C essentially. And they are bringing up, 6 months or something, change some of them. Why they are putting? Because they are more efficient things there, essentially. Maybe in terms of heat, etc., is better thing. Of course, individual person cannot do that. So that's a very reliable thing. And the cost, it is pay as you go. That is also very important. For example, lots of these companies, Wayfair or others, essentially, Overstock, name it essentially, Expedia. Some of these people, they have their own local cloud essentially. But some, like holidays, for example, like Amazon AWS has the cloud essentially. And the important cloud is mentioned is AWS, G-Cloud from Google, AWS from Amazon, Azure from Microsoft, and the other ones are like DigitalOcean. DigitalOcean is more like if you want to get some servers, etc., it's cheaper than others. There are others, of course. These are all Adobe, IBM, Oracle, all of them, they have the cloud as well. But the most innovative one currently is G-Cloud. And that is, I mean, you can do lots of things. For example, they were a bit behind AWS and Azure in terms of presenting, in terms of the computers, because it is the same thing also about Facebook. They have lots of essentially clouds themselves, but Google needs all these things for its own business essentially. It's not like Amazon may need it a bit less. It's just creating for the customers. Needs it, but not at the level that Google. Google is doing lots of computation. So any new data center that they are creating, they are using it themselves essentially for doing handling Gmail searches, etc. So they came a bit late essentially to the business. They are number 3 still, and they are actually, it was for some time it was not profitable, but now it is profitable. Recently, but they are providing some of the best tools that Google is using for searches, etc., like Bigtable, BigQuery. These are like some of the best things that they can handle very large databases. They have a very good security thing. That's the one that lots of companies are using. And as I mentioned, for example, they Wayfair. Like during the holiday, there are lots of people who are coming there. They cannot build the cloud for all these people because it would be too costly. So what do they do? Say, okay, generally we use our own cloud, but during holidays we are using G-Cloud. Some of the traffic will go there, and then for those days they are paying something to the Google. They don't need to pay all the time, essentially. This is this concept of renting that was not there before, and that is now you can use it essentially. But the basic idea was there for a long time, mainly back to mainframe plus thin clients. You need computing, peer-to-peer network essentially for a while, and client server. All of them are some basic things. Still, I mean, this is like lots of growing things and become very important cloud. So almost all programs that you write it, you should put it essentially on the cloud, including, as I mentioned, this project that you are doing here, you should try to put it on some of these clouds essentially, because then all of these good things that I mentioned, you can get it for them. A cheaper one like DigitalOcean just give you the service, the servers, but others like G-Cloud and others, they are providing lots of other capabilities on there. In addition of these guys that I have mentioned, there are 2 other companies. One is Databricks. So Databricks. And the other one is Snowflake. These are also 2 famous companies. So this G-Cloud, AWS, and Azure, these 3, they try to add more and more software on top of the cloud. So it is not only hardware, but also software. And again, mentioned, for example, G-Cloud databases are amazing. Databricks and Snowflake, they are adding even more on that. And they try to make it multi-cloud. So you may have essentially a cloud, not just on AWS, but also on G-Cloud and Azure. And what is that? Because then you may move some of your stuff essentially seamlessly if you are using some of the services that they are giving. So if this one increase the cost, then you will move to the other one, and vice versa. Databricks and Snowflake are there, but of course they are charging more for their things essentially. So this is important for the cloud essentially enable this one. So X as a service. You may do it somehow infrastructure as a service, maybe essentially the hardware stuff or like basic operating system essentially to run it. You may do it platform as a service. Platform as a service is the one, for example, the Google App Engine. It is something is a platform that you can have your app there, and then you can actually have several apps and you can do it. These 2 are more technical. More the type of thing that the people are using software as a service. It's called SaaS essentially. SaaS business generally means that these are the companies that they are providing some software for others. Generally, they can provide the software through API. You will call my API essentially, API REST essentially is the one that we will talk more about it. You will call this one, and everything is done through API REST through the internet essentially. You will save all the data here, you will request, you will ask things. For example, a database is like that. You will put everything there, you will add to the database, you will remove it, everything. This is something that is software and SaaS. this is also, you may think about, also this is used in the business, in the startup business. In the startup business, so you may have some kind of things like a startup that you are finding your cost, essentially like this kind of massive customers that you have, massive users that you have. This is the start, like Facebook, for example, or I don't know, Pinterest, lots of other these companies. These are based on the fact that you have lots of users and you try to do that. Creating a startup that is doing that at this time is more like a lottery. You are winning a lottery to be successful. Why? Because these users, why they should come to your website? How do they know even your website? Generally, you need to pay them to come to your website. And that is very costly. Who does want to do that? It's very hard, essentially, to the people are not just coming. You can have the things. The Google even does not report you. I mean, yes, some things like, for example, Threads or ChatGPT, they get lots of users over a short period, but that happens again as a lottery. Very rarely these things happen. They have the companies like Microsoft behind ChatGPT or Facebook on their threads that this happens. Not thing. They are doing lots of advertisement. Otherwise, you as a company, if you have it, then you need to pay essentially to the people, and that is very costly. The people generally don't want to invest or pay that. So that's one way of a startup. This, by the way, this is another thing that I have it with David Lowell. This is a live that I have it with David Lowell about startups. That's a very good one to see how you should think about a startup. But this SaaS also is the important one there. In the SaaS business, you provide some kind of essentially software such that other big companies generally are using it. That generally has a higher chance of essentially success. Why? Because convincing one other person in another company is much easier than convincing millions of users that they want to use for free your software, essentially. And you need to get the money, I don't know, through advertisements, etc. Yes, this person maybe is not that easy because this person is maybe VP or SVP or CEO of some company. Finding this person and talking with that is not that easy. So it's not, having a successful startup is not an easy thing. But still, is one person. You can talk about it and you can communicate. This, I don't know, millions of people that they also want to use it for free and they don't have like any, commitment to your program or your website or service is a bit hard thing. But anyhow, SaaS you may hear in terms of a startup as well. But SaaS essentially means the software as a service and the complete software. So these are the things that I have mentioned. So IaaS, essentially infrastructure, you can find examples of this one essentially, or the private or public clouds, or AWS as a cloud computing. So this is more like, yes, give you some cloud computing, but you need to do your own essentially. This is the PaaS or platform as a service. This is some kind of cloud environment that, Google App Engine, as I mentioned, Microsoft Azure and others, they are doing like, for example, Docker and other things that, or Oracle. These are some of the things that they are providing this. And last but not least are the SaaS. SaaS is like, for example, something like the Google services, lots of Gmail and I don't know, or Office 365. This is the most complete version, or the something that you will go and you are filling your taxes essentially. These are also TurboTax. These are the things that they are providing this one. So in general, X as a large, this has this one. So this one, and all of them are done through cloud. Infrastructure as a service. So it gives you the facilities, it gives you the hardware, it gives you some core things and some API that you can connect with them. In the platform, you have one more layer of integration and middleware that you can do essentially, like as I mentioned, for example, databases or etc. You can do a little bit more of essentially a bit more services essentially. Here in the this one, in the software as a service, you have a complete service. So you will keep both data there essentially, the metadata there, all the applications are there, all the APIs are there, even the presentations are there essentially. It's a complete server essentially. And as I mentioned, this, you may say X as a service. Generally the people more like software as a service is a common one nowadays. cloud types, as I mentioned, also there are two things. You may have on-premises. So this is some of the things that you have the local one, as I mentioned. For example, Wayfair, they have their own cloud. But at the same time, this is a private cloud. You may have also the public cloud like G Cloud or AWS. They don't go to AWS because these are competitors, but they go to G Cloud, for example. And they use that one. And there's a good this is some interaction between your internal cloud and outside uh, cloud. And lots of things actually it can be done by Kubernetes. Kubernetes is something that you can, this is the concept that is used essentially based on the microservices. And these microservices, you can have it, we'll talk a little bit more about it. You can have it as some of them, it might be in your cloud, some of them might be on the G Cloud, and they can communicate with each other through APIs. That's essentially the way that the whole thing seems very seamless. Another thing is this concept of data centers. These data centers essentially are the main infrastructures for that enables cloud computing. System is cloud computing. So everyone is building them, and this is a huge amount of work at deciding where you should put it there. Data centers actually, this is not just data, actually data and compute together. And this is the things. Some of this these are some of the things that I mentioned for Microsoft. Facebook, it has lots of them, but Facebook does not provide cloud for others because some of the students there said everything that they create, they use it for their own purposes. And they are making money out of it. So they don't have extra things. This was the issue with the Google as well. That Google also, everything that they built it, these are very costly. They built it, but they use it for their own purposes. So that's the thing. It is like they didn't have it earlier, essentially, the cloud business. Last but these things, we are talking about virtualizations. Concept of virtualization or virtual machine. So you may have all the time this one that you have a Windows machine, and there you have bringing some Linux essentially inside the Windows, or vice versa. You may have a Linux and you have a Windows inside. You can install Windows inside. So in some sense, in my PC, I can have both of them, like one, maybe the main one and the other. The issue is that generally when you do that, then it becomes much like the Windows inside Linux becomes much slower. The whole idea is that in some sense, what will happen? The Linux operating system somehow simulates Windows operating system. And that adds essentially more compute burden on the computer. That's generally the idea is that if you have Windows and Linux, you want to use both of them have a dual boot, such that you can do each of them separately. Because otherwise, it would be a bit, it would be a little bit slow. And sometimes you don't have the whole capability that you have it there. Because at the end of the day, Windows and Linux, they have some interaction when you go to the file system, etc. However, this idea this is one issue for this, especially because of the speed, because you can do essentially anything. Like if a computer can run Windows, a computer that has a Linux also should be able to run Windows. Because there's a set of essentially machine language that can just simulate. So that is possible by default, but maybe my laptop is not as strong enough. Because yes, the laptop becomes strong, but also Linux and Windows, they also need more compute resources. However, this is this idea that you may have a big computer, much stronger servers. So in that case, they can run this one in a seamless way. It's a very fast way. This is actually like Amazon EC2, for example, or like this. These are the big computers. And if I have a big computer, I don't need essentially to there might be some small tasks. So this is a big computer I have it, and this is very efficient. It can do everything fast. But maybe I only need a little part of it. Then you don't need to give the whole computer to me. You just simulate my task, my OS on part of this very fast computer. You may need one, you will use some part of it. So this kind of virtualization essentially means simulations, and it has some lots of advantages. So it is has a very secure ones because you have the full control on that. Everything like just think the number of attacks that happens to the Google each day or computers at Google. It's a lot, but they have a very strong firewall on that. If I want to create that one on my own computer, it would be much worse essentially. But this big computer can be a cloud computing essentially. Can be essentially part of the cloud at Google that I'm using, and it has all that security. It is multi-tenancy, as I mentioned, multiple virtual machines they can run on the same server, and it is efficiency. So you don't need to have lots of underpowered machines, small machines. You can have a big one that can simulate everything together. So these are, I mean, some of these consumer virtual machine products like VMware or the VirtualBox and others. Amazon Gen is another one that's using essentially Red Hat to do that. So this is the one interesting thing. So here is this issue is there. Like when you say that when you run it on virtual machine, maybe it's not exactly the same as a computer because still is a little bit of overhead due to these simulations. So you need to be a bit careful, but maybe in the long run, it's not a very big deal, essentially, as long as you will use it. So, and it's essentially something that the people are working more and more on that. Last slide is about the Docker. So this is the hottest things right now. And this tried one idea is that it avoids the overhead of virtualization together. I'll tell you a little bit about a story behind Docker. So Docker comes from two things essentially. Consider a virtual machine. So I have essentially this. This is the server. This is the host operating system, and here I have no on this big computer. I have like this is one person. He has his own server OS, and then it has some of these libraries etc. that is using it, and the app that is running that. I have maybe there's another computer. This is another guest operating system. All the beans means essentially binary files and libraries, and this app. But the catch is that maybe these apps, like this app B, all of them, they can just share the same OS. I don't need a different OS. I can just use the same OS. So in that sense, they are using the same version of Python or the libraries of C++, etc. So you don't need to have all these copies essentially, and then the maintenance of that would be hard. That's the whole idea. Is that you can essentially so essentially that the thing that is Docker essentially based on the concept of containerization, and the containers are isolated, but they share OS, and if it is also needed, they can share the same beans and libraries as well. So that's the idea. Essentially, that is the this is the container versus virtual machine. So you don't need all of this if I want to run it. Maybe different people are on it, but still they can use the same OS, etc., and less overhead, faster things. That's a good things about containers and essentially this Dockerization. So you have a Docker and you have a container that essentially you will put it on the server to run. Another idea also came from Python. Like in C++, you will write a program, then you have a make file, and you make an executable file. This executable file, generally on the same version of Windows, you can run it, essentially, or the same version of Linux. Some other versions may be still compatible, but maybe if the version of Windows changes, you need to create the executable. This is not the case at all with Python. Python, this is one of the things that come from the data science things, and lots of dependencies on the things. So you install one thing, this essentially needs this other library should be changed, and this library generally are written by C++. Lots of things, and if you just change one of them, it's not the correct version, the whole program does not. So this idea that so much dependencies that and lots of packages. It was not like that so many packages for C++. So which means that if you want to run this version of Python on cloud, then you need to have all of these versions. You don't want to even one difference. That's the whole idea. I said, okay, I want to run it. I will run all of this. When I make all of them as a container with all versions of that, I will say which version I want to do it. I will put all of them as the app on the server such that I can make sure that the whole thing works. So this concept of Dockerization essentially, and this kind of container. So in some sense, the same thing, because the OS is the same, all of them. Just maybe this even version is different from the libraries. That's the thing that I mentioned. Sometimes our libraries are shared, but not all the time. Maybe this is the app written by a previous version of, I don't know, Network X, and this is written by a new version. And you don't want to still make them same because there is some overhead here, and it is not easy to do that. You can, this version can use a different version of Network X, this can do it, this one. But when you do it, this version of Network X will be essentially compiled, and the important one of that will be attached to your app A, and the different version will be attached to app B. But the OS is still the same. Both of them are in Windows or Linux or something like this. So that's the idea from both of these sides that came to the concept of Dockerization. And then essentially Docker is some kind of the program with all necessary possible databases if needed, or at least all the libraries that you can run it. You will do it, and then, for example, if you use VS Code, you can just put the whole Docker essentially inside the cloud. So in sometimes cloud computing, virtual machines, and this kind of executable file is the whole idea beyond Docker. And still, I mean, there's a good progress. It may change again during the years, and from previous year, it has changed. Probably not the amount that ChatGPT essentially changed the world, but it is changing, and it becomes more convenient and hopefully easier essentially to use. Early versions were not that easy. You need to learn how you can, for example, on Azure, you can put a Docker file, or you can put a container. Anyhow, you can read more about it, and you can just, again, ask ChatGPT, say that how you can do it. It gives you the program, the example, etc., that you can do it. But at the VS Code, you can do lots of things. And again, some technicalities, but if you get it from ChatGPT or others, you can actually find the exact process to do that. Good. So we are stopping here, and then we will continue next time with the, other aspects of the data science we will talk about. People at Zoom, if you have no question, I think we are finishing the class.